ఇక్కడ నా దగ్గర ఉంది.
Blissful morning to the respected dignitaries and participants. Hope you all are staying safe. I extend my warmest welcome to each and everyone. The moment is special for us, and we all are gathered here for the day to make it more important. Myself, Sridipti, pursuing third year from the Department of Triply from SV Colleges. Welcome to a short-term training program on research trends in renewable photovoltaic system and its research challenges, organized by the Department of Electrical and Electronics Engineering from SV Colleges. Prayer. Prayer is an action. It is the process of talking with God with energy in order to achieve a purpose. So let's begin this webinar by seeking the blessing of Lord Almighty with a prayer song. Jaya Vigneshwara Namo Namo Jagadrakshaka Namo Namo Jaya Kara Shubhakara Sarvapararpara Jagadodhara Namo Namo Jaya Vigneshwara Namo Namo Mushikavahana Munijana Vandita Maya Rakshasa Madapaharana Mushikavahana Munijana Vandita Maya Rakshasa Madapaharana Manmadhari Sutta Namo Namo Vidyadayaka Namo Namo Vignavidaraka Namo Namo Visvasrustilaya Karana Shambho Vimala Charitra Namo Namo Jaya Vigneshwara Namo Namo Jagadrakshaka Namo Namo. Once again, welcoming you all. Now, I take the pleasure of inviting our dynamic, hardworking, and a supportive true leader, none other than Dr. N. Sudhakar Reddy, sir, Principal of SBCE.
Thank you, Sridipti.
Welcome,
Thank
sir.
you so much for your prayer song and introduction. And very good morning to one and all. And hearty welcome to all the participants and faculty members of Triple Department, SV College of Engineering, and convener and co-convener Dr. K. Kumar and Dr. K. Sudhir Reddy for organizing this STTP. And first of all, my sincere thanks to AICTE for sponsoring this 1 week short-term training program on research trends in renewable photovoltaic system and its research challenges. I came to know that we got very good response throughout India and some of the participants from abroad also. And we got very good response from all over India. And my sincere thanks to all the resource persons. We got very good and eminent resource persons from reputed universities, NITs and IITs. Thank you so much for organizing this program. And once again, my congratulations to Department of Triply, SV College of Engineering for organizing this 1 week short-term training program. I hope all the participants will get enough knowledge about renewable photovoltaic system and its research challenges by participating in this 1 week STTP. I sincerely requesting all the participants to participate actively in this 1 week program, and please don't absent and make this session more interactive and gain knowledge. Thank you so much for providing me this wonderful opportunity.
Thank you, sir. Now, Dr. K. Sudhi, sir, HOD of Triply Department, is a man of distinction and a fountainhead of illuminating ideas and inspiration to all of us. Welcome, sir.
Thank you, Deepthi. From our department, I once again welcome all the participants for your patience and for eagerly waiting for this STTP phase 1. So we promise you from our end, we provide the quality resource person with quality tools. So we already planned all the 3 sessions in such a manner. So it will go with the starting from the renewable sources to the grid integration, microgrids, and smart grids. So I can say from the basic level to the recent advanced techniques. So we are going to cover all the challenges, different technologies, soft computing methods. So everything we are going to come across in all the 3 phases. So I promise you, if you have a patience and attend regularly for all the sessions as per the AICT rules and regulations, so you're going to really become a good, you can also become a resource person, and you can gain more knowledge in our stream, including the latest smart grid and including the communication technology also. So I thank you each and everyone who shown the interested towards our STTP. Thank you once again. I request all of you please hold for a few seconds. Our today's resource person, uh, Dr. Dastagiri Reddy sir, is about to join the session, and sir will take up the 2 sessions today, because we personally requested sir to take up the session and begin the all our 3 phases, because sir has more experience in a real-time manner as well as in a research also. Uh, I'll request everyone please hold for a few seconds. Thank you.
Good morning, sir.
Sir, good morning, sir. Sir, just give us a few seconds. Our Deepthi is going to give your introduction. Deepthi, I request you to please go through the staff profile.
Yes, sir. I consider it a great honor to talk about our chief guest, Dr. B. Dastagiri Reddy Garu. Dr. B. Dastagiri Reddy Garu is assistant professor at NITK since 2019. He has awarded PhD in Electrical and Electronics Engineering at NIT Tiruchinapalli in 2016. He has completed his master's education in Power Electronics, JNTU University 2011, and his BE in Electrical and Electronics Engineering at JNTU University 2009. Mr. Reddy had a mark in the field of education. It is our privilege to have him as today's resource person. He made a mark in the field of administration as R&D engineer at ABB JSPL, Chennai for 2 years and as a research fellow at NUS. His areas of interest are power electronics, microgrids, e-mobility, HVDC, FACS, condition monitoring, and reliability studies. He took 5 patents, 2 commercialized, and 3 field. He published 7 international journals and attended 12 international conferences. Sir has obtained Certificate of Achievement in TOIEIC test in 2007. Sir has trained and participated in SCRUM methodologies in 2018. He has obtained Group Lean Six Sigma White Belt in 2018. A person of such magnitude truly inspires us. His guidance and presence is a source of great motivation for us. We really privileged to have his presence with us in our AICT sponsored 1-week short-term program. Welcome, sir.
Thank you, ma'am. Thank you for the kind words.
Thank you, sir. Now, I would like to hand over this session to Dr. B. Dastagiri Reddy Garu.
Yeah. Thank you, everyone, and good morning to all. Firstly, I would like to thank HOD and organizers for giving me this opportunity. And today we'll be talking about solar PV, starting from very basic. So let me share my screen first, and please let me know when you can see my screen. Is it visible, ma'am? Hello? Hello?
No, sir, it's not
Sir,
visible, sir.
Sir, can you share your presentation, sir? Pin on presentation, sir.
One second, sir. Um, Sir,
So,
I think I don't have
can
the
you?
permission to share the screen.
No, sir. You have, sir. It is showing as you're presenting, sir. So, can you present your whole
Okay.
screen, sir? Entire screen.
Yeah, I'm doing that. Okay.
Now it's loading,
How,
sir.
what you
Yes,
can
sir.
see?
Sir, it's meet. It's a meet window, sir.
Okay. The slide will be coming
Yes.
up.
Now it's coming, sir. Yes, sir.
Okay, sir. All good? Hello?
Yes, sir,
Yes,
it's
sir.
good,
Now
sir.
it's visible, sir.
Okay. So sorry for the mess, participants. So we'll start in a while. So today we'll be talking about photovoltaic technology and systems. So we'll start with the basics of sunlight, then what is the property of sunlight, how we are able to get the energy. Then we talk about selection of material for PV panels, and then we talk about how it works exactly. Then we enter into what happens if there is a mismatch in cell, what about partial shading. Then we talk about systems. Okay, so it will take roughly around 4 to 5 hours, but I'll try to stick to the time given by the organizing committee. And for the benefit of participants, so I don't want to enter into the general knowledge, like how many installations are there in India, in or all the world, what is the futuristic view of solar. I'm not going into that. We'll be directly jumping into the topic. So this is the overview of my presentation. So I'll be talking about what is energy, energy conversion, then solar energy, what is the properties of light, then based on that, how we have to decide on the semiconductor physics. Then we talk about a diode operation, then solar cell operation. Then we'll be mostly discussing about how these IV characteristics, then this modeling of PV panel, then we enter into the systems and mismatch losses and everything. Okay. Yeah. You can always interrupt me whenever there is a doubt or concern that you have to clear out. Our participants or the organizer, request the organizer, if there are any questions pop up in the chat, please let me know so that I can clear then and there itself. Well, so since we are talking about energy, power, that is electrical power, so I thought it's good to start with what is work, what is energy, and what is power. So we all know that work is involving two things, force into distance. If you want to move something for a distance of 5 meter or 4 meter, so definitely you need certain force and also some mass. So for example, if you want to move 20 newtons, if you want to use force of 20 newtons and push an object for 5 meters, then the work is 100 joules per work. What about energy? Energy is you should be able to have that much of energy to do that work. So basically the units are same. To do 100 joules of work, you must spend 100 joules of energy. Then here comes our interesting topic, that is power. So the power is the rate of work of, or how much you're, in what rate you are utilizing the available energy with you. So 1 watt is 1 joule per second. So if you take this second to the other side, so you get 1 watt second equal to 1 joule. And that's how you get 1 unit of power is equal to 3.6 megajoules. Okay. Please take a note of this particular value because we'll be revisiting this particular equation once again, so that we can relate what is the energy available in the sun and then how it is related to the number of units that we can generate. Okay, so 1 kilowatt equal to 1 kilowatt hour, that is 1 unit is equal to 3.6 megajoules. Okay, now there are different energy conversions available out there, but we are very much interested in electrical energy. So in what are the different ways of conversions possible to get electrical energy? So we start with the chemical energy into thermal energy, then thermal to mechanical, then mechanical to energy, and you can look at the efficiencies. So it will come around 45 or 50, roughly 50% of efficiency. But there is other way. You can directly get electrical energy from chemical by using fuel cells, and efficiencies are around 60%. Okay. And there is another way, that is gravitational or hydrodidal. You can use the gravitational energy and you can create that difference in heights, and that you can convert that into mechanical energy and mechanical energy to electrical energy. That is also possible. And we also know about the nuclear. So nuclear fusion reactions can generate a lot of heat. That is thermal energy, then thermal energy to mechanical energy, then mechanical energy to electrical energy. And here comes our renewable energy sources, that is wind and solar. And we know how to do that. So wind to mechanical and mechanical to electrical. And from solar, it is possible that you can go generate a thermal energy from thermal into mechanical, mechanical to electrical. That is also possible. But there is a possibility from solar to electrical. And that is nothing but your PV. We'll be talking about this in a couple of hours from now. Fine. So just to give you overall idea, like how many kinds of PV panels are available out there and what are their efficiencies. So you can have a look at this particular figure from National Renewable Energy Laboratory. So that is NREL. You can follow this page if you are interested in working in renewable energy. So it will give you all the data, all the products and whatnot. So you will find a lot of interesting stuff here. So if you look at these colors, so these are multi-junction cells. And this color that is blue, that is crystalline silicon cell, that is monocrystalline cells. And there is something called green, they are thin film technologies and emerging PV technologies as well. So if you look at multi-junction cell efficiencies are always higher than the blue ones. You look at this efficiencies around 46%. And every point in the chart tell you who has come up with this one. For example, if you take at this point, at this year, NREL has proposed one multi-junction cell. So every point tell you either the laboratory or the institute who has proposed that particular PV panel and what are their efficiencies as per the year. So you can get huge information here. Now in this presentation, we'll be talking about not one in particular, but we'll be discussing how multi-junction is possible, how to select this particular semiconductor devices and whatnot. So I'll be talking about the basic uh, research and challenges in selecting the components and in designing the components as well. Okay, so there'll be little bit mathematics involved here and there, but don't worry about that one. So I'll be uh, going through in a better way so that people can be comfortable. Okay, so this is the electrical data of a PV panel. When you purchase a PV panel, this is what you can see at the back side of the panel, or even you will be, I'm sorry. Yeah. So basically, I want to start with what is this STC. So all these ratings, whatever given, it is valid for standard test condition, which says irradiance 1000 watt per meter square and module temperature 25 degrees centigrade. I think this is quite straightforward. Everyone know about this. But what are these two terms, irradiance and AM, that is air mass 1.5. So to know that, we need to know something about solar or sun first at the instant. Then we will talk about what is this power, maximum power, open circuit voltage, short circuit current, and whatnot, everything. So first we'll talk about what are these standard test conditions, and that's how we proceed further. Okay, for that we need to know about the significance of solar. So as you all know, sun is the source of everything. Sun is the source of wind. Because of sun, there is a wind. Because of sun, there is hydro. Because of sun, there are many things, and we have seen all the conversions that is possible to get an electricity from that. So it is good to know what is sun and what's happening there. So basically, a sun, what's happening there is a fusion reaction is happening there, where hydrogen is converted into helium, and as a result you get around 20 million degree Kelvin. But fortunately, we are not getting that much heat at the surface because most of the heat is absorbed by H ions, and you can see that at the surface it is around 6000 Kelvin, which is close approximation to black body radiation. Okay, so whatever the heat generated there will be radiating into the space. Okay, so how it radiates and what is the energy available in that? Okay, some fusion reaction is going on at the sun. Why do I care? So why you have to care is when it radiates, you get a lot of energy. What is that energy and how can you tap on that energy? So that is the main focus here. Okay, who gave that formula? It's Einstein who gave that formula. The energy associated is E equal to mc square, where m is the mass lost. But while with fusion reaction, there will be some mass losing by sun. So if you calculate that one, it will be roughly 3.8 into 10 to the power of 20 megajoules is available at the sun. Okay, what does that mean? We know that we have seen 1 kilowatt hour or 1 unit is 3.6 million joules. Then what will be the how many units you can generate? And if you are curious, it is like total installed capacity in India is 386 gigawatt. Uh, I think this is with respect to 2019 March. That's what I looked at, but there may be an update. I'm not sure. So that would be roughly around 3.8 into 10 to the power of 9 kilowatt. Okay, so now you can imagine how much energy is available out there. But we are not getting this much of energy because we are quite far away from the sun, and there will be some losses in between. So we'll look at how much energy exactly we are receiving. Okay, for that we need to know that there is a fraction of radiation that is coming out of the sun is received by the earth. We'll see what is that. Okay, so to generate energy from sun, which is quite abundant, there are some factors affecting that. The first one is the spectral content. So what is the amount of radiation we are receiving? That is the first thing. Then what is the energy in that particular spectral content? For example, if there is gamma rays, X-rays, infrared, everything is available, but we are getting only visible. So in that visible range, what is the amount of energy that will be receiving by Earth? And then we know about the panel direction. We have to keep the panel in particular direction. So that direction is also matters. And also the location where you are talking about. Are you talking about India, that is especially Tirupati, where the current event is happening? or are you talking about America? Are you talking about Australia? So it depends on various factors. So various factors will be uh, I think you'll not be able to seeing the screen. I'll be sharing it again. Um, can someone let me know if the screen is available? Hello?
Now it's coming, sir.
Okay.
Sir, can you do this slideshow, sir?
Yeah, it's already there, I think.
Yes, sir. Now it's coming, sir. Thank you, sir.
Okay. Yeah. Fine. So we'll talk about all these things in a while in a greater detail. So we know sunlight is emerging as an electromagnetic wave, and we have a lot of wavelengths available. As I said, there will be gamma rays, X-rays, UV rays, but fortunately we'll be seeing only visible spectrum. Okay. So in that visible spectrum, we need to know what is the amount of energy available there. Okay. For that, we need to convert that energy in terms of electron volt. So why we are interested in calculating energy in terms of electron volt? Sorry. Why we are interested in calculating the energy of a photon in electron volt? So you'll be wondering why we talked about joules and now he's talking about electron volt. So the electron volt is important in deciding the semiconductor material. Okay. So I'll be talking about the dots here and there, and then finally I'll try to join all the dots here. Okay. So by using Planck's constant, we can calculate the energy associated with the individual photon that will be depending on the wavelength. So if the wavelength varies, then the energy associated with the photon available in that particular light will be varying. So that's how you get uh, this constants. So I'm not going into the math. So I'll be talking about visible spectrum. Okay, so we know that it starts from 3.8, that is roughly zero point 0.4 micrometer, and see the photon energy is 3.09 electron volt. And for the wavelength of 0.7, that is the red light, so you'll be getting 1.7 electron volt. Okay, yeah, I think again there is an issue. I'll start broadcasting again. Um, Sir, is there any reason behind this? Is this a problem from my side? Why it is stopping at every 10 minutes or something?
Uh, so not like this. So I request participants, please turn off your video because the video takes more pixel, more packets, data packets.
Okay,
Please cooperate with us.
okay,
So now it's visible, sir. Thank you, sir.
yeah. If someone is wondering what is this electron volt, that means if you want to push an electron against 1 volt, for example, if there is a barrier of 1 volt, then if you want to push an electron above that one, the energy required is 1 eV. So that will be roughly 1 electron volt equal to 1.602 into 10 to the power of minus 90 joules. Okay. So the important takeaway from this slide is every photon available in the visible spectrum has some energy. Okay, and that energy that's what we calculated here. That is in blue light, it is 3.0995 electron volt, and in the red light it is 1.77 electron volt, but in between it will be ranging from 3 to 1.7. So that's the amount of electron volt available for one photon. Okay, just available for one photon. Then what is the number of photons that is available, that we need to calculate now. Okay. The for that, we need to know the photon flux and photon power density. So the value we have seen, that 3.77 electron volt, that is the energy available in one photon. But we will be receiving a bunch of photons. So for that, we need to define these constants, that photon flux, which will tell us about how many photons you are receiving per second in a square meter of area. Okay, so I'm not going into too much of mathematics again. So let me tell you, if you say that if it is 3 into e to the power of 21 photon flux, that's the energy, then it will be power density will be 961 watt per meter square. Now we'll be able to relate what is this watt per meter square, how it is coming. Okay, so the standard operating condition tells you it is 1000 watt per meter square. This is where it is coming from. So it is coming from because there is an energy at the sun, and the sun is radiating into the space. Unfortunately, we are not receiving all the radiation, but we'll be receiving only visible spectrum. In the visible spectrum, there is a photons of energy. Each photon has certain energy, from starting from blue light to red light, and then from blue light to red light, there will be like one photon having that much energy. But if there is a bunch of photons coming to you, then what will be the energy with that one? So that is why you are getting 1000 watt per meter square as a standard operating condition. Okay, but if you look at, if the energy of the photon changes, see the variation in the power density. Okay, so everything is important. How many photons you are receiving and what is the energy of the photon. So I just changed one value here. So I just changed 2 electron volt to 1 electron volt, but I'm receiving same photon flux, but see the power has reduced a lot. Okay, and similarly, if I reduced 3 e power 21 to 3 e power 20, and you can see the variation in the amount of watts that you'll be receiving in a 1 meter square area. So that's the significance of the photons that you receive. Okay, whatever the photons you receive is really a huge thing to decide on the panel construction. Okay, now coming to the actual thing, that is spectral irradiance. So we talked about individual photons. In the individual photons, then if a bunch of photons of same wavelength is coming, but we'll be getting from 0.3 to 0.7. So we have to integrate everything to get the total energy associated with every photon of every color. So blue light, there is some bunch of photons. Red light, there is bunch of photons. Violet, there is some bunch of photons. So if you want to calculate the energy, then definitely you have to go for integration. So with that integration, you'll get the total energy associated like this. So if the temperature of the black body varies like this, if it is 1000 and from wavelength 0.1 to 100, this is how the watt per meter square changes. Okay, but we know our sun's radiation is around 6000, that is 5777 Kelvin, and we are receiving only in this range, and that is why we are taking that as 1000 watt per meter square. Okay, that's about irradiance, how you are getting that one. But again, we are having a distance from the sun. Okay, and the radiation varies with inverse square law. So for example, at the surface there is a huge energy, but by the time it reaches certain distance, it will come down, because in the previous slide, if you have seen that at the surface, see the energy, it is 10 to the power of 8 watt per meter square. But this is not we are receiving, because we are far away from that, because of this formula where H is inversely proportional to the distance between the two bodies. Since we are quite far away from the sun, and this inverse square law comes into picture, and that's how different planets receive different watt per meter square. Okay, Earth will be receiving 1366.1 watt per meter square. Wait, we were discussing that it is 1000 watt per meter square, but actually we are getting 1366. So what happens to that 366? That is because we have some effects. That's wobbling effect, we'll discuss in a while, and also there will be atmospheric pollution everywhere. That is also an and causing to reduce this 1.3 kilowatt hour to 1 kilowatt hour or less than that one. So we'll discuss that in a while. Okay, so the power variation due to elliptical orbit itself is 3.4%. And also there will be atmospheric effects. So there will be ozone layer, upper dust layer, air molecules, water vapor, lower dust molecules. So all these things scatters the light, and finally you get some reduced amount of light that is coming to the panel. Okay, so these and all matters. Everything atmospheric effects, whatever I discussed here, that is ozone layer, upper dust layer, and the percentages are clearly shown here. And there'll be scattering. Because of the scattering, it lose some photons. So finally, the amount you receive is less than 1366 watt per meter square. Okay. Then we'll talk about air mass. What is this air mass? So air mass is the ratio if you receive the light directly to a point, but if you receive the same light from an angle. So that's the difference. This ratio of light intensity that you receive if you are straight ahead of that point, or if you are at an angle at that point. So that ratio gives you air mass, because we never expect always your sun is directly on your head. So it will be moving here and there, even including the total Earth. Take the total Earth, it is also because it will be having some angle variation. So that is why we generally go for 1.5 rather than 1, because we cannot expect sun is always straight to the panel or straight to the earth. So it is moving here and there. So average, it is taken as 1.5. Okay. If you see, like, for example, if there is a light coming here, it is straightly here. So then it will be 1 here. But if your location is here, then it will be scattered like this. So that is why most of the time it will be taken as 1.5 as standard operating condition. But if you are wondering what exactly is it, then you have to find out the angle. Then you use this formula, you will get what is the exact AM in your particular location. Okay. But most of the panels are tested with 1.5. Fine. So we covered most of the part. Sorry. I think this time the issue is from my side, because any doubts so far, organizers? Anything in the text or chat?
Sir, up to now, no questions, sir.
Okay, madam.
Uh,
Give me a second. Yeah. Okay. So if you take AM as 1, you will be roughly receiving this much of energy, that is 2 kilowatt hour, 2 kilowatt per meter square. If it is 1.5, you will be restricting to 1.3 or 1.5. So average with this area under the curve. So it is going here and coming down. So you have to take area under the curve. So that's why it will be considered as just 1 kilowatt watt per meter square. And coming to the position of the Earth. So we know that our Earth is tilted like this, and then it started rotating in elliptical orbit. And because of that, it will be having a wobbling effect. What does that mean? So the convenient reference, if you take Earth is fixed, Sun is moving, so you will be talking about this variation from June to December. We'll see that one in a while. Okay. So for example, if your house is here, in June, your sun path will be like this from morning to evening. But in December or January, it will be like this. Uh, I'm sorry, I don't know what's happening here. I suspect it's because of
Sir,
too
it's
many
visible.
GIFs.
It's visible for us, sir. PPTs are visible for us.
Okay. Okay. Uh, Maybe because of so many animations, sometimes it is shutting down. I shouldn't have used so many animations. Sorry about that. So, to summarize whatever we discussed so far, there is so much of energy available at the sun, and but unfortunately, we are receiving that one. There will be like too many impacts on that one. Uh, Now we come across what is the total amount of radiation that will be irradiation that will be receiving at the particular location. But above that, there is something that you need to take care about the position of the angle. So in which angle that my uh, panel should be placed. For that, we are trying to get the background why I have to keep that angle in this position. So that's the reason behind going to this different angles. That is the declination angle, elevation angle, and azimuthal angles. So basically, what I'm trying to tell you is the sun is not taking the same path every day. For example, if it is morning 6 o'clock, the sun rises and sun sets. If you look at in December, it will be some location. If you look at in uh, June, it will be in some other height. So the height variation. So that is what the declination angle tells you. So in June, you will see it is at the maximum height, but in December, it will be at the lowest height. It may not cross this line, but it depends on the location. If you are in southern hemisphere or northern hemisphere, or if you are near to the poles, it happens like this. Okay, so these angles are very much important to decide. Basically, what I'm trying to tell you is these angles are very much important so that by using these angles, you'll be able to decide what should be the inclination of my panel and in what direction that I should keep the panel. We'll come to know that in a while. Uh, Maybe this will be better for you to get an understanding. So today, that is October 19, your sun's path is like this at Tirupati. Okay. In June, sun will be taking this path. So sun rises here and it goes. See, the sun is around 55 degrees, not 90 degrees. You see nearly 90 degrees only in the month of April for this location. Okay, for this location, that is Tirupati, right? So these charts are available online, so you can go and have a look at it. Now, what I should get from this part, like why I am so much worried about this one. Now, if you see in January or in December, you see the angle is 50 degrees here, but the same at 12 o'clock, the angle is around 90 degrees. So I need to take care of these things because it is very much important that my panel should be facing the sun. Okay, but I cannot change the panel for every day and every hour. So is there a method that we can get rid of all these things, or is there a method that I can take care of all these variations? We'll see that in a while. So there will be again some mathematics involved here. For example, your location is latitude north. I think if I'm not wrong, at Tirupati it is latitude 13 degrees centigrade. So you have to place, I mean, the animation shows here it is latitude 15 degree north. So that means you are in southern hemisphere. So most of the time, your sun will be in the north side. So it won't go beyond that one. Let's try to play this one. So this graph tells you what is the incident power. The blue one tell you what is the incident power. And if you change the panel direction, for example, this module power, the green one. So when I'm changing the angle, I mean, when I tilt this panel, you can see how the power varies in the module. Okay, so my tilt angle is 31. That's how it changes. Okay, so the position at which the panel should be placed is calculated here by using all these formulas. Let it run. So if you place the tilt angle 60 degree, you see the power that you can generate is very, very less. So when should I change this angle? Okay, so at 0 degree, if you are keeping it flat, at this instant, you will be able to match the blue line. So the blue line tells you what is the maximum amount of power you can generate. And the red line tells you if you don't use any angle, that is 0, just you play on a plane, you just kept the planar, that is about a red one. The green one tells you if you play with the angle, how it varies. Okay, so the suggestion here is you have to change the panel in every 3 months once. Okay, the first, to match this curve, it should be some angle, and to match the end of the curve, it should be one angle, and the rest it should be another angle. So that's the best way to install your panel, having 3 different angles. So one angle for first 3 months, and then rest for quite a long period. Then for the last 3 months, it should be changed again. That's how you can exactly get the blue curve. Okay. So when you are installing a PV panel at your premises or house, you ask that particular guy who is installing to give you a slot so that you can change the angle at least 3 to 4 times. So that is the best way that you can extract more power from the solar. And what is the best angle to, instead of not doing anything, if he says, no, that will be expensive, so I'll give you a fixed angle, then what is that angle that you should look for is what is your latitude angle, then fix that angle. For example, if the latitude angle is 13.4, then you fix the panel as 13.4. And to which direction, whether to be east or north direction, that is what your azimuth angle or inclination angle tells you. So all you need to see about whether it is towards south or towards north. In India, it is towards south. That means the downside will be south, the upside will be north. So you'll be placing north to south with an angle. That angle is your latitude angle for the if you don't want to change the angle in the year. But if you want to get more power, then you have to change it 3 times in a year. So one, you need to use this formulas and calculate in which months I have to fix one angle to match this curve. And then even if you keep it in flat for a few months, then it will be no issue. Then for the rest, you have to change once again. So in a year, you have to change 3 times the position of the panel so that you can get more power. Okay, I hope I'm clear. Fine. Now, in which location, how much maximum power that I can get? We have seen what is the impact of solar inclination angle, panel inclination angle, or panel uh, position. Now we'll see at different location what will be the difference in solar insolation or irradiation received in a year. So basically, again, there will be some videos that I will tell you about from day one, that is January 1st to December 31st, how it varies. But we may not be so much interested in that, but I'll directly tell you what is that peak sun hour. Okay. So most of the days, sun rises like this and sun goes to maximum point, maximum elevation angle, and then it comes down. So then what mathematicians done is you can do some approximation. So you can convert this area under the curve as a simple square so that it will be easy. And that's how they said by calculating all this area under the curve, they said it will be having this much of peak power in so and so time. Okay, so that is how the peak sun hours came into picture. So by calculating the area under the curve and based on the location, they decided, okay, this is the maximum peak hours that in this location you can get. And if you are wondering, in India, this is the chart. Okay, so if you see in those areas, red color, the peak sun hour is around 8.88 hours. That means you get 1000 irradiance for 8 hours in a day. Okay, what does that mean? If you look at this 8 here, so in that areas you get 8 hours the peak radiation, that is 1000 watt per meter square. If you look at Andhra here, somewhere here, it will be 5.5 to 6 hours. So if you have a PV panel, if you are correctly placed that PV panel in right angles and right direction, then you will be getting, for 5 hours, you will be able to get 1000 watt per meter square. So that's talking about these things. Okay. So I hope you understood what is this irradiance, how it came from, what is this air mass. And temperature, anyway, it's all know, understood. So what we covered here is what is happening at the sun. Total energy, it is 3.8 into 10 to the power of 20 watt per meter square is available, but unfortunately we are not receiving that much because of spectral content of the light. So we'll be receiving only visible spectrum. In the visible spectrum, there are photons, and each photon has an energy. The blue photons has some amount of energy, that is 3.077 electron volt. And for red light, it is 1.7 electron volt. So why we are interested in electron volt? Because that is what the energy required to move an electron. Okay, so why electrons in terms of EV? That because we need to select the material. Okay, that we'll see in a while in the next session. So not in the next session, in a while. I want to give a pause for some time just to have any discussion here. So we'll be moving to semiconductor physics now. So any doubts in terms of inclination angle, how to calculate that one, and what is the position that you have to keep, anything in the chart? Otherwise I'll go to the next PPT. And also please let me know if I'm going too fast.
Sir, up to now, no questions, sir, in YouTube and chat box also. I think we can proceed
Okay,
for
madam.
other slides.
Okay, maybe as an organizer, you can tell me like whether it is too fast, too slow. Or...
It's okay, sir. Everything is understandable. We are following that one.
Okay.
Thank you, sir.
Okay. So okay, madam. Shall I proceed with the second one? Are you able to see my screen?
Sir, screen is not visible, sir. Presentation is not visible.
Maybe loading.
Yes, sir. Now it's visible.
Okay. So we have looked about this irradiance part and everything. Then we'll be talking about semiconductor physics. Now we have to decide on what semiconductor material that I should use as a PV panel. Well, in this presentation, I'll be talking about different materials, carrier concentration, charge transportation, PN junction, how it works, then how to generate this electron hole pair, what is this electron hole pair actually, and what is this recombination and everything. So I'll stop at diode operation. Then we'll proceed into what is the difference between diode and PV in greater detail. Okay. So we all know there are materials of three kinds. So I don't want to spend too much time here. So maybe quick points. So metals, you don't have any barrier here. So valency band and conduction band, there is no barrier. For insulator, there is a band gap energy which is greater than 3 electron volt. Okay. So please note this value, it is greater than 3 electron volt. That means if you want to excite an electron from valency band to conduction band, you need more energy. But this is not possible with solar radiation because the maximum energy available is 3.007 electron volt. So you cannot use materials as a solar panel, that is insulators as a solar panel. But look at semiconductor, the band gap is less than 3 electron volt, and with how you can excite this electron from valency band to conduction band by using thermal or photon. Why photon? Because our photon, we calculated the energy associated with the photon of a blue light is 3.007, with red light is 1.007, 1.77 electron volt. So that's how you can use a semiconductor. So my question to all the participants is, why not metal? Because there is no band, you can easily use the electrons into valency band and conduction band. Why not metals are used as PV panels? Okay, just think about that one. If not, we'll disclose the answer in a while. So why not insulator? That clearly understood, because you need a band gap energy that is greater than 3 electron volt, which is not available in our sun's irradiation. But in semiconductor, it is possible because the band gap energy is less than 3 electron volt, and you can use that one. By photons, you can excite an electron from valency band to conduction band. But when it comes to metals, there is no band at all, there is no band gap. Then why can't the metal be used as PV panel? Why you are running behind semiconductor? That's the question. Okay. So if you look at the periodic table, generally we go with single crystalline means, then it will be, you'll be using this group 4 elements, that is silicon and germanium. That is monocrystalline panels. You'll be using these materials, I'm sorry. Okay, the crystalline structure is shown here. And polycrystalline everything, it is a combination. Okay, from group 3 to group 4. Either you can use AIP or GAAS. GAAS is available commercially, and then INSB, a combination of group 3 and group 5. So that's how you get polycrystalline PV panels. That is GAS shown here. And there is another possibility, that is group 2 and group 6, that is cadmium and telluride. You can also use a combination of these materials as a PV panel. I mean, as a semiconductor, and that semiconductor can be used as a PV panel. Okay, I think it has stopped again. I'll go and present it. Madam, any response in the?
No response, sir. Up to now. No questions. Sir, you are not audible, sir. Oh,
And I also observed that if someone try to share their screen, then my screen automatically goes off. So if someone unknowingly clicking that option, then it will be an interruption for me as well.
yes, sir. We have instructed all the
Okay.
participants. Okay, sir. You can proceed, sir.
Yeah.
Yeah. It's visible, sir. Your
Okay,
screen
madam.
is visible.
So what you see, madam, like band gap of semiconductors, that's the slide you can see.
Yes, sir. Yes, sir.
Yeah. So I was talking about different semiconductor materials and the lattice constant, that crystalline structure I was showing. So I'm not going into details of crystalline structure, but here is the reason behind that one. So based on the lattice constant, you will get this band gap energy. And you see all this diamond, the band gap energy is 5.5 electron volt, which you cannot use as a PV panel because the energy associated with our blue light to red light is in the range of 3 to 1.77. Okay, so we cannot use that one. So whatever the material you come across, the semiconductor material, which can fall under this category, that is 0 to 3 electron volt band gap, then you can use that as a PV panel. Okay. So if you want to do a material research, you can come across different combinations and see that your band gap energy is less than this, then you can go ahead and try out for PV panel. Okay. And also there are some other things to take care, but this is the first thing that you should look at it, that is band gap energy. Okay. And if you look at the band gap energy of different materials, it's shown here. So this band gap energy varies with respect to temperature as well. So for example, at 0 degree, it is 1.17 for silicon. For 300, it is less. Okay, that is at room temperature. Roughly, it has come down. So for everything, it applies the same. At room temperature, the value of band gap energy will be less. So that's how you have to decide on what is the semiconductor that I have to use. So if you are looking at monocrystalline, so it will be mostly based on silicon or germanium, mostly silicon, not germanium so far. But if you are looking at polycrystalline, then it is a combination of group 3 or group 5, group 2 or group 6. So this is how you select the semiconductors. Okay. Now, what is the trade-off that I should take? What happens if the band gap is more? So that means your voltage, internal voltage will be more, but the current will be less because to energize one electron, I need more energy. So if you have less energy, then you cannot energize more electron. Energize electron in the sense nothing but the current flow. So if you have smaller band gap, then your voltage is low, but current is high. If you have higher band gap, then your voltage is high, current is low. But we are worried about power, which is a product of voltage and current. Okay, so that's why generally we decide on the band gap energy should be roughly around 1.2 electron volt to 1.3 electron volt. So most of the PV panels will have a band gap energy of 1.2 electron volt to 1.8 electron volt. Okay, this is because if you have higher band gap, that means higher voltage within the band gap, but low current. So voltage into current will be less. Then if it is smaller, then your voltage is less, but current is more. So we are worried about the product, which is V into I. So it is decided that it is good to go with 1.2 electron volt or 1.8 electron volt in this range. So most of your PV panels will be ranging in this fashion. Okay, now we'll be talking about some intrinsic concentration, like how these electrons and holes with respect to 0 degree, with respect to 300 room temperature, then how you have to change, what is the need of doping and all those things in a while. Okay. So we all know that the intrinsic concentration is constant. That is, if you take any atom, there will be number of electrons and number of protons will be always equal. So that is what the intrinsic carrier concentration, and this product of electrons and holes or protons, it is n square. That is what called mass action law, and you don't have to worry about too much about this definitions. But if you are really interested in doing the calculations, then you have to go very deep about that one. But anyway, I'll run through what are the takeaway points from the every slide so that it will be easy for participants to follow. So here what I'm trying to say is, if you take a pure metal or pure material, the number of holes and number of electrons are equal. Okay. Even at room temperature at 0 degree, all your electrons will be at the valence band, and conduction band, nothing will be available. But at 300 at room temperature, maybe some electrons will try to fly to get some energy from that room temperature, and it will be useful for 3 or 4 electrons to go to next level. That is what you can do. Okay, so but still the ratio remain same. You cannot change the ratio. Then what about the conduction? How electrons and holes conduct or move, and how it moves? There is two ways of movement. One is diffusion. So when there is a space available, it try to move, but the net movement is zero. Okay. But when you have an electric field, then we know that the hole, which is positive charge we consider, it will move along the direction of electric field. And for electron, it moves the opposite direction of the electric field. Okay, so these two are very important because diffusion is the one useful in diode operation. Drift is the one used in PV panel. So if you ask me directly, what is the difference between diode operation and the PV panel? Both are more or less diodes, but the conduction in diode is because of diffusion. The conduction in PV panel is because of drift. Okay, and to answer my question why metals are not used, you cannot generate an electric field within the material that you use. So if you don't have electric field, that is voltage V is zero in metals. You have a lot of current, but V is zero, so the power is zero. So you can have movement, but it doesn't have any directions to go or any voltage to go. So that's why you cannot use a metal as PV panel. But in semiconductor, you will be able to create a potential difference within the material itself. That is what acting as a V for our external thing. Okay, we'll see that in a while, how you can create a internal electric field. Okay, so this is the movement. So diffusion is the reason behind the diode operation. Drift is the reason behind, or the main operation behind PV panel. Okay. So why we need doping? So we all talk about doping. We know that is doping is simple, adding impurities. What exactly it is doing? So it is disturbing that number of electrons and hole pairs should not be equal. If it is equal, you cannot do anything. But you should make a difference. Then only it is possible to create some electric field between them. We'll see how we can do that. Okay. So to create built-in electric field to improve the conductivity, that is the main reason behind doping. Okay, it's not just adding impurities. So adding impurities means that you are disturbing that N equal to P relationship, and that's how you can improve the conductivity. Also, you can able to create built-in electric field. So that's the main reason behind doping. And let's see how to do doping. So for example, if you have a silicon, which is 4 electrons with it, I'm just showing the 2-dimensional view, but it is actually a 3-dimensional view. To dope, we know we get one P atom. If you place it here, you see there is one extra electron here, which is free, and it moves here and there, and that's how this P gets positively charged. Okay, when you lose an electron, you get positively charged. So you are disturbing the number of holes and number of electrons. If as long as they are equal, you cannot get positive charge or negative charge. Either there should be a difference. That's how you can end up in either a positive charge guy or a negative charged guy. Okay, so that's the reason behind doping, to disturb the N equal to P relationship and to create a positive charge and negative charge. Okay, when it comes to P doping, you go with less number of electrons. So you have an extra space available for some electron to occupy. Because of diffusion, one electron will try to move from there, from the next atom to here. So that's how it gets one more electron here. So that is why it gets negatively charged. So to get a positive charge and negative charge, either you have to that we already know. So what exactly it is doing is you are creating an additional layer energy band so that you are able to easily excite from here to here. Okay. So initially it was from valency band to conduction band, but because of this doping, you get an additional energy level, that is donor energy level, which can give you more electrons. So on the total number of the relation between N equal to P is disturbed, and that's how you'll be able to get a positive charge or a negative charge. If it is a donor level, you'll be having more electrons. The same way, if you are having acceptor, then you will be having the other way around. You will be providing more holes to that. Okay, the acceptor level. So I don't want to go too much details about this one. So the main thing is you are disturbing the mass action law. You are disturbing N equal to P relationship, and that's how you are able to create a positively charged atom or material and a negatively charged material. So that's happening here. Okay, the p-type doping and n-type doping, what is happening here? So mathematics, I don't want to go through here, but the takeaway points I already explained to you in simple words. Why? Now electron hole densities after doping. So what you see after doping is in p region there will be lot of extra holes available, and in n region more number of electrons available. Without doping, number of holes and number of electrons will be same. There is no positive charge or there is no negative charge. But here after doping, p region have negatively charged and n region have positively charged. So that's how you created this one. Now what happens? If you look at the ratios, you disturb that one. Basically, it was equal. Majority and minority carriers was equal. With the doping, you disturbed that one. The majority carriers by minority carriers is 10 to the power of 16 per centimeter cube to 10 to the power of 4. If you are talking about exact number, what it is. Right. Now, coming to PN junction. So when you bring two junctions together, then what happens? Because of diffusion, some electrons and holes try to recombine. Okay, then you get a additional voltage build up here. It was already charged, positively charged and negatively charged. When you brought it together, then because of some diffusion, there will be some exchange of electron and holes and it will disappear. Then you will left out with positive and negative. So that's how you can create internal electric field, which is only possible with semiconductor, which is not possible with metals. So that's why you cannot use metal as a PV panel. Okay. So once you get this field, what I can do with this? Okay, I got the field. So what's the purpose of this one? So that means you have created internal voltage now. Now you have to create the current flow. So you have a voltage and you have to create the current to flow. Okay. We know that whenever there is an extra electron hole pair on both sides, what happens? Because of this electric field, we have seen that the holes will be moved to the other side, that is in the direction of electric field, and the electrons will be pulled to the other side, which results in abundance of electrons in this side and more number of holes in this side. Now, when you try to join these two like this, then these abundant electrons will try to flow from here. And if you connect a load here, that's how you get a current to flow through the defined path that can be your load. Okay, so you have to select a semiconductor such that your band gap should be less than 3 electron volt. And we also discussed about what is the range of band gap, what is the significance of selection of band gap, why semiconductor material, all these questions. So why semiconductor material? Because it can only create, there is the only way to create internal electric field without doing anything. Okay, you just have to dope something and put it together, you get an electric field. With that electric field, you will be able to generate. Whenever there is a new electron hole pair generation happens, then as shown here, when there is a new electron hole pair generated, what happens? You get exchange. So you get abundant electrons here, then abundant holes here. Okay. Now the question is how to generate this electron hole pair. Okay. And if someone having a doubt, what is this electron, what is this hole? It's very simple. For example, if you are taking out an electron, that means there is an empty space available there. So that is nothing but the hole. So these two are linked together. You cannot create only holes. You cannot create only electrons. It is always a pair. So it's nothing but you take out an electron, there is a space available for some electron to occupy. So that means you are losing an electron, so it becomes positively charged. You are getting an electron because this electron, whatever you moved, will be received by someone else, that becomes negatively charged. Same simple thing. Okay. But he is eagerly looking for a place to settle down. For that, we provide a path so that this guy can come and settle down its original position. Okay, so that is what the analogy that I can think of and explain in a better way. Okay, so coming back to the original question, how to get this electron hole pair, that is you can increase the temperature, or you can increase more number doping, and finally you can also use photons to get an electron hole pair. We have seen that we disturb that number of electrons on hole by doping. We have seen that one. We also know that with the temperature it is possible to create electron hole pair at a normal room temperature. Few electrons jump to some other place and it may come back again. So that we have seen, but now we'll look at how we can excite an electron by photons, okay, or create an electron hole pair using photons. So for that, we all know these different collisions, like the photons of energy which is equal to less than band gap energy. You cannot excite this electron to move to conduction band, that we know. If the photon energy is greater than, then you can excite this electron to conduction band. But if it is too much, then it tries to come back and it will radiate some energy or this. But now you have to decide what is the photon energy that you are getting, whether it is equal to the band gap energy or less than or greater than. So in that way, you have to decide the semiconductor material and place it. Let's see how to do that. These are the research challenges. In what way you have to decide the thickness of the PV panel, what should be the N layer, what should be the P layer, how thick it should be, where should be the exact junction should be lying. So these are some research challenges that I'm going to discuss in few slides. Okay, so there is something called absorption coefficient for different metals. For example, if you take silicon, the red one, it tries to absorb this wavelengths of light. Okay, we know that visible spectrum having a wide range of wavelength, that is 0.38 to 0.7. So if you look at how deep or how much that particular light to pass through. And then to excite an electron, the light has to pass through inside. So a different material has different coefficients. You have to look at that coefficient as well. It's not only band gap energy, but also you should also look at this coefficient called absorption coefficient. How much light can be absorbed by this particular semiconductor material you selected. So that is also an important phenomenon. If you don't observe properly, then the photons cannot enter inside. If the photons cannot enter inside, you cannot create an electron hole pair. In simple words. And how deep it can go, like inside, for example, my thickness of the metal is 1 centimeter. So how deep it can go, that is also important. So we'll be discussing these things as well. And this is the reason behind why you have to worry about this one. For example, you have blue light to red light, all variations. If the panel allowing all the lights, then this is how it looks. So all the blue light will be absorbed at the terminal itself, but red light can penetrate more because it is having more nanometer, I mean micrometer of wavelength. So different wavelengths of photons will be absorbed at different levels. Okay. Now, when you talk about the multi-junction PV panel, what you are doing is you create one junction here which can utilize the blue light and you generate some electrons and holes. But the other light, which is other colors of light, which is passing through without doing any job, what you can do is you can have another layer of junction here, so that that is how you can effectively utilize all the photons available in all the colors of light. In 7 colors, you have blue, which is having a highest energy, which will be utilized at the top layer itself. But other, technically it is called as tandem of cells. Okay, and there will be some generation of how many wondering that values, numerical values, you see at the surface, you'll be able to generate 10 to the power of 20. But if you go deeper into the material, so it drastically reduces. Okay, so you cannot use a PV panel of 1 centimeter thickness. This is the reason behind that. It should be very, very small. We'll be talking about in mic comes down drastically 18. So if you use 1 centimeter, it's no use. You cannot utilize that material like silicon, whatever you are using. It will be waste. Okay. So this is talking about how the generation rate happens. So light absorption has major effect on yes. Okay. So this is one takeaway point here. First takeaway point is the thickness. You'll be once you generate electron hole pairs, which has a major impact. So right, once you generated electron hole pairs, what is the possibility of recombination? Recombination means you are asking a guy to go away, but he just asks some guy. To my knowledge, till now only silicon is being used extensively. There may be other reasons behind it, maybe the material availability and the manufacturing cost for that. So far, I have now not come across any other material when it comes to monocrystalline. Only silicon is extensively used.
Yes, sir. So another question, sir. What is the main difference between PN diode, photodiode, and solar cell?
Junction, I think we have already covered. So it is because when you apply a positive forward bias, then the junction between the two junctions, the PN junction will come down. So the diffusion current will dominate, and that's how it conducts. Then the photodiode is you excite that electron from the other side to cross over by giving some energy. Okay, so that is what the electron volt talks about. So the electron volt EV, for example, if the barrier is one of energy from somewhere, either you can get it from photon or you can raise the temperature. That's how you give an extra energy for that electron to move against the electric field. We know that electric field all, but if you want to move against that one, that energy is given by the photons.
You can unmute yourself and you can ask directly to those persons.
A certain slide and look at the mathematics of that one. That is also fine with me. If there are any general questions, I'm open to take that one.
I think no one is coming forward, sir. No one is having the
Okay.
dots. So I request.
Maybe I can summarize because there is some more time. It's 11:17.
Yes, sir.
Maybe I can summarize whatever so far we have covered. So we covered about sun.
Yes.
Okay, there'll be so much of energy. Yes, madam, you want to say something?
Yes, sir. You can continue, sir.
Okay, so we talked about sun's irradiation. So what is happening at there? So there is a fusion reaction and there'll be tremendous amount of heat. So when there is a huge amount of heat, then it will radiate into the space. So that radiation is coming as an electromagnetic spectrum. So in that spectrum, every wavelength of the wave has certain energy. But fortunately or unfortunately, fortunately because we are surviving with when there is other radiations are not coming to us. Unfortunate with respect to the power. So there will be so much of power that you can generate, but you are limiting to visible spectrum alone. Okay. So that's why I said fortunate for human beings to survive, unfortunate for the power range that you are able to generate. So only in the visible spectrum you'll be having certain energy. So that energy is for a blue light photon. It is 3 electron. It is 1.7 electron volt. So you will be receiving a bunch of photons in blue, bunch of photons in red, bunch of photons in violet, bunch of photons in indigo. So all this bunch of photons, if you summarize or integrate the energy associated with every photon of every color, then you will be receiving 1366 watt per meter square. But what happens to the 1300? There will be, so the total amount that you receive is approximated as 1000 watt per meter square. So that means if you have a 1 meter square area, like 1 meter length and 1 meter breadth, so you whatever, but that is not actually happening because of so many reasons that we discussed in the semiconductor physics. Okay, you are getting 1000 watts, but how much you are able to utilize that 1000 watts and how much you are able to actually capture that one depends on many factors. So the many factors is how you laid your panel. Okay, how you laid your panel. So for the panel position, we have seen its wobbling effect. That means your sun's position changes day by day. Every day it changes. Okay, now you have to look for what is the best angle that you have to decide. So we discussed that one. What is the reason behind that? And we also concluded that if you want to extract more energy, you have to change the panel in 3 times in a year. Okay, 3 times. The best angle is latitude if you want your angle. Since we all are in India, so we have to face that panel from north to south. Okay, north side the panel should be upward and down should be in the south direction. So it will be north-south direction with an angle of inclination equal to latitude angle if you want to fix the angle throughout the year. But if you want to get more energy, you have to change that one for 3 times in a year. Okay, that we have seen that. Now, for every location, their sun peak hours will vary. Sun peak hours from morning to evening, how the sun rises, sun sets, and based on the location, there will be a calculation behind that one. So that it is approximated as sun peak hours. So it depends on the location, the sun peak hours vary. So for example, if it is 5 sun peak hours, that means during 24 hours, only 5 hours you can have 1000 watt per meter square, or that is the maximum amount of power that will be received. Then after that power receiving to you, then it is up to the panel efficiency, panel inclination angle, everything comes into picture, and what is the energy that you can generate. Okay, that's about solar irradiation and air mass also we have discussed. That's about property of sunlight and what is the amount of power that we are receiving per square meter. Right. Now we jumped into semiconductor in the next slides. So we talked about why metals are not used because it doesn't have the capability of generating internal electric field, which is nothing but the voltage of the PV panel. So you cannot have a voltage within the metal. No matter you do anything, you cannot get a voltage inside a metal. So that's why you cannot use metals, though there is plenty of electrons available for you. Then when it comes to insulators, the band gap energy is slightly higher, that is more than 3 electron volt, which is higher than the energy of the photon available with you, that is with the sun. So you cannot use insulator. Then obviously the other option is semiconductor. So semiconductor, you cannot use a semiconductor directly, number of electrons and proton holes or protons. Then for that you need to go for the doping. So doping increases the conductivity and doping helps you to generate internal electric field. Okay, 2 things: increase the conductivity and increase the or create the internal electric field. That's about the doping. So once the doping is done, then when you place the 2 junctions together, because of the diffusion, there will be barrier comes into picture, then there will be no more movement of electrons and holes to the other side. But if you want to move, then the one way is to apply electric field, which is opposite to the internal electric field. That's how you close the barrier so the diffusion can happen. Or you can use photon energy to excite an electron to cross over. That is what electron volt tells you. The electron definition of electron volt is 1 electron volt represents the energy required for an electron